Let's talk about the input data to develop the simulation or using the simulation model. So input data has two types. One is the deterministic input, another one is a random input. And randomness of the data is very significant, especially when we develop the simulation model. Let's consider the one machine finite queuing system, so MM1 queuing system. If the input data, let's say the service time is constant and the interval of time between entities is constant, then we can call that the data itself is deterministic. So interval time is 1 minute and service time is 0.9 minute. Sorry. So in this case, let's say interval time of entities is 1 minute and then service time is a 0.9 minute. Then that means there will be no part in the queue or no entities will be queue, right? Will be in the queue. Because the service time is smaller than the interval time between entities. So the service of the previous entity will be finished, right? Before next entity enters the system, right? So according to this data. So under the deterministic input data, there will be no part in the queue. However, let's say input data following the stochastic property. So for example, interval time is following the exponential distribution with the mean of 1 minute, and then service time is following the exponential distribution with the mean of 0.9 minute. In this case, because these two, because in service time, we are not sure about exact service time, right? So sometimes service time can be even greater than 1, or way smaller than 0.9 and so on, right? Because it's following the exponential distribution. So interval time also same thing. Sometimes interval time between part can be less than 1 minute, for example 0.5 minute or 0.6 minute and so on, or greater than 1 minute, right? Because it's following the exponential distribution with this mean value, right? So there will be many parts in the queue at some point, right? Also maybe there is no part in the queue at some point as well. So that's why, by having this kind of different data set, actually, even though mean value are same, but if you have a stochastic model, basically, it's a kind of difficult to estimate the status of the system at a certain point, right? Due to the randomness. Right. So anyway, we are dealing with the system having randomness, right? So usually our input data is usually associated with a certain distribution, or for example, normal distribution, something like that. And here are data types to be collected for the simulation development. So one is time, such as interval times, processing time, and traveling time. And also you can have probabilities. And so in previous model, you already put the probability value, right, in the decide module, right? So in this case, you can see how many percentage of gold, silver, or regular customers can enter the system, or you can also consider the demand of each part, right, and so on. That's a probability. If you look at the model for 3-1 in Arena, and definitely we know that how many parts should be, or what percentage of the part should be scrapped or salvaged, right? So you need to have that kind of product value. Also, sometimes you may need operating parameters such as a conveyor speed, bus speed, and so on, or physical layout, the length, okay, for your simulation development. Yes. So, okay. So let's say you have a data, collected data, and then you need to develop the distribution, basically, right, based on the collected data, right? So there are two types, actually, the types of distribution you have. And one is an empirical distribution. You can use the data directly, basically. Yes, based on the given data or collected data, you can develop the distribution, okay? Or you can use a theoretical distribution. Let's say, so in this case, based on your collected data, you can find the most fitted theoretical distribution. Okay, so in this case, you need to find the parameter for a certain distribution. Yes. All right, so empirical distribution case. So let's say you have input data of 5 points. So 5 data points, 1, 2, 1, 2, 1. Okay, you have 5 data points here, and then we can develop the PMF, right? So this is a discrete data set. So you can develop the PMF based on this data. So when x value equal, or when x value equal to 1, equal to 2, and then you can calculate the probability, right, for each case. So first one is 0.6, next one is 0.4, right? So summation between these two cases will be 1, right? So according to the definition of probability. And then CDF will be what? So when x equal, so x, the CDF will be 0 for any x less than 1, right? And then also will be 1 any x greater than or equal to 2, right? So, and then if x, okay, is equal to 1 basically, and then definitely from this point until this point, actually your probability will have a CDF will be 0.6, right? So this is the shape of CDF. And if you use this distribution directly, yes, we can say that we are using the empirical distribution, okay, based on the given data. Okay, so in ARENA, if particularly when you use a discrete distribution, empirical distribution, you can use this syntax, DISC, okay, and this means 0.6 at when x is 1 and becomes 1 when x is 2. So this should be CDF, okay, when you use the DISC function, empirical function. However, continuous case is slightly different. So let's say you have 5 data point, 0.1, 0.2, 0.8, 1.3, 1.9, so real numbers, okay? And then definitely you can develop the PDF, right, with the range. So when x is between 0 and 1, and then definitely it should be 0.6. So how many points we have? 1, 2, 3, right, over 5. 1, 2, 3 over 5, yes. Yeah, so that's why 0.6. And then if x value is greater than 1 and less than 2, then we have 2 points out of 5, right? So our probability value will be 0.4, right? So summation between these two events, I mean these two events will be 1. Okay, so based on the PDF, you can develop the CDF, right? CDF function. This is the shape of the CDF function. So it's just starting from 0, right? Fx is start from 0, and then it will increase as the value of x increases, right? And then up to 0.6, and then from the 0.6, it will also become 1 when x equals 2, right? So according to this and these two values, okay, and then this, yes. So this is the shape of CDF, and then when you use the continuous empirical distribution, you can use this keyword CONT. So previously we used the DISC, right? DISC, right? As a function of the discrete empirical distribution, but this one is a CONT, right? And then your parameter should be like this: start from 0 when x equal to 0, and then becomes 0.6 when x equal to 1, and then becomes 1 when x equal to 2. So all these number, so probability value first, and then x value, so probability first and x value, and the probability, comma, and x, okay? Right, so when you use this function, your function will have this kind of shape, okay? All right, so if you don't like to use empirical distributions, continuous or discrete empirical distributions, and then definitely you can use theoretical distributions, okay? And ARENA actually provides a software called Input Analyzer to develop to develop theoretical to find the most fitted theoretical distribution for you, and then based on the output result of the input analyzer, you can actually you can identify which distribution is the most fitted, and then use that distribution in your simulation model. It's just simple, right? Okay, so step 0, yeah, let's say you have the data file, or so extension of the data file can be text file, txt, or .dst, and definitely I provide you the file, so you can just directly download the file and then run the input analyzer. And also since I provide tutorial, and you can do that too, right? So let's say you have these 30 data point, okay, and then once you have data point and open input analyzer, and then create your new project, you have to create a new project and then load the data from a file. So if you go to the file and data file and click the use existing option, and then definitely you can have this kind of view. Okay, and here's a data summary. So number of data points is 30, right? And then mean value, max value, and so on. Or you can get the summary of your data set, okay, from input analyzer, right? And then after you analyze your data point using the histogram, and you can also choose, you can identify the most fitted line. Okay, but before you do that, you can also change the intervals of the histogram. So if you go to option parameter histogram, and then definitely you can change the number of intervals for your histogram. So currently we have 5, and the low value is 3 and high value is 5. So you can actually specify the histogram. Okay, and if you increase the number of intervals, and basically you will have a slight different shape. Good. Okay, and then once you have, but you don't have to change any histogram shape, and actually, because input analyzer will automatically generate the histogram for you. And then by clicking the fit all function in input analyzer, you can identify the most fitted line, and even it give you the arena expression. So here's a triangular distribution, right? This given data actually is most likely have a triangular shape, right? So triangular distribution with these 3 values, parameters, 3, 4.4, and 5, will be the most appropriate distribution, theoretical distribution, can be used in arena. So you can just use this expression, tria, okay, 3, 4.4, 5, shown here in the arena. Good. Yes. And here's a histogram display, and then distribution summary. Also, when input analyzer identify the most fitted theoretical distribution, it also conduct the chi-square test and Kolmogorov-Smirnov test for you. Okay. And here is the distribution summary of the given data. What data? Actually, I already give the data, right? So this data, okay. Once you have this data, and you will have this summary in your input analyzer. So distribution type is triangular, expression is a tria, 3, 4.4, 5. Okay, and scale error is 0.005125. So you can see the difference between the theoretical distribution and then the histogram developed by your data set. So yeah, this is a scale error between those 2 values. And chi-square test result is here, and the Kolmogorov-Smirnov test result is here. And in case that you cannot remember the meaning of these 2 tests, and I will explain the actually chi-square test as well as the Kolmogorov-Smirnov test. Okay, in the following slide. Right, so let's look at these three, I mean the two tests and then mean square error, okay? And mean square error actually is a minimal, smaller value is a lot way better, okay? Because there is small value itself is the error. So if you have a small error, that means it's a theoretical distribution. It's most likely to be exactly same as the collected data set has just following the theoretical distribution without any error, right? If you have a very small error, right? So that's why. So let's look at the mean square error and average of the square error terms for each histogram cell, basically. So if you look at it, the blue line is the theoretical distribution, okay? And then these 5 bars are histogram, right? Bars in the histogram. And in order to calculate an error, so you need to, not you, so input analyzer, to calculate the difference between the histogram and then fitted probability distribution. So these are the error, okay? Errors, and then scale the errors and add all the errors. That's all, okay? Good, and then take the average. Got it? So that's a mean square error. Okay, so and then you can also conduct the goodness of fit test, and then you already knew this, right? So if you already took the statistics courses, and then you already knew how to use how to conduct this goodness of fit test, right? Right. So let's say you want to we want to test formally the following the hypothesis. So data follow the specified distribution or theoretical distribution, or the data do not follow the specified distribution or theoretical distribution. Okay, so null hypothesis and alternative hypothesis. So we have these two hypotheses, and then so in chi-square test, so we can test these two hypotheses actually using the chi-square test and then Kolmogorov-Smirnov test. That's what you call goodness of fit test, right? All right. So in chi-square test, actually, you can initially you can divide the range of CDF actually in k intervals, and then let's say nj is the observed frequency count, okay, for the jth level of the categorical variable, and then ej is the expected frequency count for the jth level of the categorical variable. So this is observed frequency, and this is the expected frequency. In other words, this is ej is given by what? Given by theoretical or specified distribution. Good. And step 4, you can compute the test statistic, so chi-square value. So here you can subtract the ej from the nj and then scale the value and divide that value by ej, okay? And j is from 1 to k, so you can consider all k intervals, okay? Of course, smaller value is better, right? So if you look at this is kind of error, right? nj minus ej, the difference between the observed frequency and expected frequency. So if you have a small error, and then definitely all chi-square value will be very small, right? Yes, so chi-square will be small if CDF is actually your distribution has a good fit, okay? Reject H0 at H0 at level alpha. Okay, alpha usually is 0.05 or 0.1, right? If p-value is smaller than alpha, right? That means, if you go back to the previous slide, if you reject H0, that means data do not follow the specified distribution. So if you have a higher p-value than alpha, then you can accept H0. So actually we want to accept the H0 in this test, right? So data follow the specified distribution. Okay, let me go back to the previous example. So if you look at it, let's say we are using 0.05 as the alpha value, and then corresponding p-value is 0.48, 0.81, right? Which is a way higher than alpha. So we can accept H0, right? In other words, you can use triangular distribution, this distribution, in your software instead of using the empirical to actually instead of empirical distribution, or you can use this distribution to represent the characteristics of the collected data. Good. So just check the p-value in chi-square test. It should be greater than alpha. All right. And we have an example. So here we have an example. So let's look at this. So collected service time is 0.5, 0.8, 2.3, and 3.9. We have 4 data points. And then to understand the distribution of the service time, you can actually conduct the chi-square test, right? And let's say we want to check whether this data point following the uniform distribution shown here, okay? And so interval is given, right, for you already. So start from 0 to 4, right? We have 4 intervals. And then conduct the chi-square test at alpha 0.05. And our criteria, okay, chi-square value is 7.81, okay? And first of all, when you have this kind of problem, and then you need to calculate the nj value, ej value, right? Because you know that we have 4 intervals, 1, 2, 3, 4. So we have 4 intervals, and then based on that, and you can actually calculate nj as well as ej. And nj is very simple, right? You can just count the number of observations for each interval. So first interval is what? Between 0 and 1. So we have 2 data points, right? Between 0 and 1. So you can type 2 here. And then next interval is between 1 and 2. And we don't have any number. So put 0. And third interval between 2 and 3. 2 and 3, we have 2.3. So you can type 1. And then 3 and 4, between the 3 and 4. And we have 3.9 here. So our observation, or frequency will be 1, right, out of 4. So 2011 will be the value of the nj, right? Okay, what about ej? Ej, actually you need to calculate the value, right? So ej is calculated, right? If you multiply the probability for each interval, probability of each interval by the total number of observation, which is 4, and then you can calculate the expected frequency, right? So 1 times 1 over 4 will give you 1, or 1 times 0.25 will give you 1, right? And then not 1 times, 4 times, sorry. And then 4 times, again, 4 times 1 over 4 also give you 1, and then 4 times 1 over 1, 4 times 1 over 4 also will give you 1. Also 4 times 1 over 4 will give you 1, right? So yeah, but in this case, yes, if you know the property of the uniform distribution, and you can easily calculate the ej value, right? Uniform distribution, in other words, all intervals should have the same number, right? Same frequencies. So you can just put the 1, 1, 1, 1, because we have 4 intervals and 4 observations. So that's why. Okay, just please note that summation of nj and the summation of ej should be equal, should be the same. Okay. All right, once you have value of nj and ej, and then you can calculate the chi-square value, right? So for the first interval, you can subtract 1 from 2 and then scale the value and divide this value by ej, right? E1, E2, E3, E4, right? Because we have 4 intervals, so we have 4 terms. in case that you don't remember the definition of chi-square, and then let me show you the equation. So here, right, we have four intervals, so k value is 4 in our case, right? So start from 1 up to k, right? Okay, so that's how you calculate the chi-square value. Once again, n1 minus e1 square, and divide this value by e1, also the n2 minus e2 and square, and divide this value by e2, and so on. Okay, if you calculate all the numbers, and these two are cancelled out, right? 0, 0, and then this is 1, this is 1, so chi-square value will be 2. However, this value is smaller than or equal to rejection criteria, so you need to accept the hypothesis, null hypothesis. So good fit, you can use this uniform distribution. Okay. All right. So let's talk about Kolmogorov-Smirnov test. It's a similar test. It's quite similar to the chi-square test. So you can choose one of the tests actually. All right. Step 1. You can develop the empirical distribution, which is fx, right, from the observation, and then also develop the fx hat based on the theoretical distribution, or specify the distribution, and compute the test statistic, which is a d. Okay, so subprime, and then between fx and then fx hat. And definitely d should be small, right, if fx hat is a good fit, right? And then reject a0 at alpha level if d exceed 1 minus the alpha quantile as given by this ks table. Okay, so let's look at the previous same example. Okay, we have the 4 data point, and then also uniform distribution here, right? Subject uniform distribution here, and then ks test. You need to conduct the ks test, Kolmogorov-Smirnov test at alpha 0.05, and then D4, when you have 4 data point, D4 rejection criteria is 0.624. Okay, so which is given by this table here, 0.624. Okay, all right, and then draw the fx and fx hat, right? Of course, this blue line is fx, and then this orange line is fx hat, right? Given by theoretical distribution, and find the highest error, right? Interval error between at each interval, and then over the multiple interval, and we know that this value is what? So the fx when x equal to x equal to 1, and fx at when x equal to 1, right? So you can subtract these two numbers here and there, and then 0.5 minus 0.25, right? And then absolute value of this gap, this difference, it will be 0.25, which is smaller than or equal to 0.624, right? So what? Good fit, right? Because this value is smaller than the criteria, right? Rejection criteria, that's why. Okay? Right, so either way, you can directly use this test statistic, or you can also use a p-value, okay, given by the test statistic, this one. Right.